Hello, Chem students. This is Professor Ship, and I wanted to give you guys an overview about atomic notation, isotope notation, and atomic calculations. Let's get started. So, on your screen, you see an example of what's called atomic notation. But what I'm going to do is give you all two different examples on how to understand what atomic notation really is. So what you notice on your screen is that you have the atomic notation, and they're giving you some key components of what you need to know regarding that. So of course, at the very top, the number that you write at the very top.
So as you see the numbers on the top, you have your mass number. Remember I said it just doesn't mean just any particular mass. It is a calculated number based on the protons and neutrons. And then on the very bottom, you have your atomic number, okay? So let's go ahead and go through this so I can show you step by step how all of this is going to work, okay? I'm going to have a blank screen so we can go through some examples. If you take a look at your periodic table, let's say you're looking for, let's say, sodium, okay? I want you to tell me, and again, you're going to be basically saying this to the screen. Look at sodium. I want you to tell me the number of protons, electrons, and neutrons, okay, for just plain sodium. Now, you're probably wondering, all right, Ms. Ship, well, where am I going to find it? It's on your periodic table because every element that you see in the box, okay, will have the chemical atomic number, the chemical symbol, of course the name, sometimes they don't, sometimes they will, and then you will see a mass number, okay? And it could be very, very long, but we're just going to keep it short for this particular part of our video. Now, at the very top, that 11 right here that you see represents the atomic number. It also represents the protons and the electrons, okay? And if you remember the acronym that I told you, PEA, then you will not forget that that number will be written 3 times. Now, when it comes to writing your atomic mass number, we must round this number up to the nearest whole number, which will be 23. So over here, my protons are going to be 11. My electrons are also 11. With my neutrons, I'm going to say 23 minus 11 to give me 12. Now, how do we write the atomic notation for the information that's been provided? Well, all you have to do is look at your periodic table once again and write the chemical symbol. At the very top, I'm going to look at that 23 and put the 23 right there. Okay. And on the very bottom, I'm going to put my protons, which is 11. This, ladies and gentlemen, is the atomic notation. Now, to write the isotope notation, it's real simple as well. You're going to write the chemical symbol dash 23. So what both of these notations have in common are the mass numbers, okay, the 23. But how they're different is based on this particular notation over here, the atomic notation, requests that you write the atomic number. So as you can see on the screen here, as you look at the atomic notation for silicon, notice how silicon is written up here, okay? We have 29 over 14 Si. But if I told you to write the isotope notation for silicon, you would write Si dash 29, okay? It's that simple. Don't make this hard. Just concentrate on 3 numbers, the protons, electrons, neutrons. Now, in terms of isotopes, an atom of the same element that has a different number of neutrons in the nucleus are called isotopes. Now, let me kind of rephrase that again so you can understand what we mean. Because isotopes have the same atomic number, but different mass numbers. Okay, so let's look at the example of, let's say, hydrogen. If you look at your periodic table for hydrogen, hydrogen has a mass of 1. There's also a such thing as hydrogen 2. And then there's also hydrogen 3. Now, how are they the same? Well, they have the same atomic number, which is the same thing as the protons. So if I were to rewrite this, okay, I would write 1 at the very bottom for hydrogen 1. I would write 1 at the very bottom for hydrogen 2. And I would write 1 at the very bottom for hydrogen 3. But what I'm going to write at the very top is the mass number. So in this particular case right here, I know that hydrogen has 1 as the mass number. But over here, I have a 2 for hydrogen 2 because that is the mass for hydrogen 2. That is an isotope for hydrogen. And then the last example is hydrogen 3. Now, let me again explain to you that isotopes just pretty much means that it is the same element, but it has a different mass number. And if the mass numbers are different, that means the neutrons are going to also be different. How do I get my neutrons? Well, remember, all you're going to do is subtract these two numbers. So 1 from 1 gives me 0. So the first hydrogen here has 0 neutrons. But when I go over here to the next one for hydrogen 2 has 2 minus 1 to give me 1 neutron. And then the last example, for hydrogen 3, I have 3 minus 1. That's going to give me 2 neutrons.
There's something else I need to point out. Not all elements have isotopes. And as you take a look at this particular chart here, just the first 10 elements alone shows you that. If you noticed here on the left side, right here in this particular column, you see 2 1s. Okay, that's for hydrogen. Now, what they're showing you are the naturally occurring stable isotopes. But you remember previously I showed you that hydrogen actually had 3 isotopes. But again, just to kind of keep things in perspective, not all the numbers will be provided. However, I do want to point out that there are some elements that do not have isotopes. And the first one on the chart, beryllium, right here. See that? Beryllium only has 1 mass number, and that's the number that you see on the periodic table. If you move on over to fluorine, right here. Fluorine also doesn't have an isotope. Okay, so what you need to keep in mind is that not all elements have isotopes, and if they don't, the number that you see on the periodic table is that actual mass number. However, those elements that you do see on the periodic table, like carbon, you see carbon 12, carbon 13 right here. The number that you see on your periodic table represents the average weight of carbon. It's like 12.01. So what we're going to do now is do some atomic mass calculations. Let's start. So on the screen are some practice problems that we're going to do as it relates to atomic mass calculations. One thing you must remember is that you will multiply these 2 columns right here. But the other thing you need to keep in mind is that whatever your percent number key is here, you have to move your decimal back 2 places to the left. Okay? That's one thing you have to keep in mind. You will move your decimal back 2 places to the left. So I'm going to show you how simple this can be. You're going to write the 68. Hold on one second. So let's continue with these examples. So the first one deals with gallium-69 and gallium-71. The first mass that you see here is 68.9256, and the percent abundance, you're going to multiply these 2 together, okay? And remember, significant digits are here. They did not go anywhere. So 68.9256 times 0.6011. Now, where did I get that 0.611? When you move your decimal back 2 places to the left, okay? That's where we got that. Now, when you write this particular number out, once you multiply those 2, you're going to have to put your number in 4 significant digits. So let's go ahead and calculate this out. 68.9256 0.9256 times 0.6011 gives me 41.43. Now, the next one, you're going to do the same thing. You're going to say 70.9247 times 0.3989. Again, you have to move your decimal 2 places to the left, okay? And when you multiply those two numbers, remember, your answer must be in 4 significant digits. In this particular case down here, I would end up with 28.29. Now I'm going to add these two together. So 41.43 plus 28.29 gives me 69.72 atomic mass units. And if you look at your periodic table for gallium, that is going to give you the exact number on that chart, okay? And that's how you know if you're doing the problem correctly. Let's look at the next example, where you have carbon 12 and carbon 13. Let's see here. I want to use a different color so we can have a different look. All right, here we go. We've got 12.000 times. Again, you're going to move your decimal back 2 places to the left, 0.9889. Now, again, I'm going to multiply those numbers, and your sig figs must be in check. Remember, you have you have 5 significant digits in this number, and you have 4 significant digits here. So when I multiply these two numbers, I'm going to get 4 significant digits. I have 11.87. Now with this number here, I'm going to still move my decimal back 2 places to the left, and I'm going to insert a 0 there as a placeholder. So I'm going to get 13.003 times 0.0111. Again, I have 5 significant digits here, but in this particular case, I only have 3. So when I multiply those two numbers together, I'm going to end up with 3 significant digits in my final answer, which in this particular case, I get 0.144. And when I add those two numbers together, okay, I get 12.01 atomic mass units for copper. Now, if we look down below here, okay, we have one more example. I'm going to let you try it, but remember, whatever you get for your answer, it should equal to the mass number of copper on your periodic table. Okay, and just to give you heads up, some periodic tables may give you 63.55, some may say 63.54, and some other numbers, but the key is to make sure that your final answer has the correct sig figs according to your calculations. All right, if you have questions, please reach out to me or leave your comments below, and we will go from there. Have a great one.